Okay, here we go for exercise 10E question 9. Part C is obviously very difficult. You know it's difficult because it's got 7 marks on it. I'm going to go through parts A and B in quite a lot of detail because that's going to help us with part C if we understand that fully. Okay, a car of mass 900 kilograms, 900 kilograms, pulls a trailer. And because it says pulls, I'm thinking there's going to be something with tension in it. Okay. Of mass 300 kilograms along a straight horizontal road. Okay, so it's just going to be straight, it's not an incline. Using a light tow bar. I don't need to worry about the mass of the tow bar if it's light, which is parallel to the road. The horizontal resistances to the motion of the car and the trailer have magnitudes of 200 newtons and 100 newtons respectively. Okay, so I always get a bit confused. I need to read that a couple of times. So the car has resistance of this, and the trailer has a resistance of this. Okay, and that's going to oppose the motion of those things. Okay, hopefully this will make sense when we do a diagram. The engine of the car produces a constant horizontal driving force of magnitude 1,200 newtons. Right. Show that the acceleration of the car and the trailer is 0.75 meters per second squared. First things first, diagram. So here we have the car and here we have the trailer. And that's being pulled along by a horizontal tow bar. Okay, well this is interesting because it's not a light inextensible string this time. This means it's a solid thing. So this can both have tension and thrust. Right, let me just label the things that I've got on here. So this thing is, I'll just write it. This thing is the car. The car. It has a mass of 900 kilograms. This is the trailer. It has a mass of 300 kilograms. Okay, now let's think about what's going on now. So what else did the question tell us? It said that the car produces a constant horizontal driving force of 1,200 newtons. Let's label that on. So that's going to be 1,200 newtons. What other things do I know? I know that let me read it again. The horizontal resistance of the car and the trailer are this and this. So car is 200. Let's label that on. I know that the car, because its resistance, it's going to oppose the motion, is 200 newtons. And I know that the trailer also has a separate resistance, and that's going to be 100 newtons. Now, as we discussed before, just like it is if it's a light inextensible string, I know that there's going to be, the car is being pulled. So if I think about it, there's going to be this tension here, which is the trailer. The same tension, it's going to be completely the same value as this T here, is the thing that's pulling the trailer forward. These two tensions will cancel each other out. Okay, that's a bit misleading. They'll cancel each other out if I look at the whole system, just to make that clear. Right, and then the other thing I just need to consider is it's moving in this direction and it's accelerating in this direction. Show that the acceleration of the car is this. Okay, so I'm going to look at the whole system. And the reason I'm going to look at the whole system is typically it's a bit more straightforward. Because if I do that, as I said a second ago, the tensions are going to cancel in this bar. So part A. I am going to resolve, so I'm going to look at the whole system. And then I'm going to resolve in the horizontal direction. And that's going to give me the following. So let's think about the forces acting in this direction. If I've said this direction is positive, I've got 1,200 What forces are acting in the opposite direction? Well, the 200 and the 100. Again, I could do minus T plus T, but those two would cancel each other out. So this is the force, the resultant force. That's equal to the mass, so the total mass, which is 900 plus 300, because I'm looking at the whole system, times the acceleration. I don't know what the acceleration is, but I've got everything I need there. If I just rearrange that to make A the subject, we should get A equals 0.75 meters per second squared. That's a nice question because it even tells us what it wants the answer to be. Right. This would be a really inefficient way to solve this question, but I'm going to discuss it with you because I want you to understand it. I might, if I wanted to, have answered question A like this. I might have looked at the forces on the car alone. Yeah, so I'm going to look at the forces on the car. Forces on the car are as follows. Didn't mean to cut that bit off, sorry. So that's going to give me 1,200 in this direction. And then against that is just going to be the tension this time and the resistance of the car. And that's going to be equal to the mass, which is 900, times the acceleration. Can you see from this, it doesn't help me because I've got two unknowns. I've got a T and I've got an A. So a really long-winded way to do this, but it's important that we understand this, is to look at both, I won't call that B to confuse you, is to look at the car, and now I'm going to look at the trailer. Yeah, now I'm going to look at the trailer. So let's look at the forces acting on the trailer. So I should have made it clear that I was resolving in this direction. And I'll do the same with this one here. So look at now, I'm just going to look at the forces acting on the trailer. So the force pulling it forward, the only one in that direction, and I'm calling this positive, is T. And the thing acting against that would be just the resistance to motion. That's 100. Apologies for the handwriting. Any other forces? No, is equal to the mass, which is just of the trailer, is 300 times A. Now, as I said, this would be a much more long-winded way to do this, but another way of solving this is, if you think about it, what I've basically got is one equation with two unknowns, a T and an A, and another equation where T and A is the same with two unknowns. What I've basically got is simultaneous equations. If I wanted to, I could rearrange this one here to make, for instance, this is T is equal to 300A plus 100. Then substitute that back into this one here. Can you see that that would be a way more long-winded method to do it? So I don't think the book even goes into the detail with the stuff like that. What it will just say is look at the whole system. The reason that we look at the whole system is because unless it's asking for the tension in there, if I just look at the whole system, the total mass and the acceleration is constant because they're connected, I don't have to worry about working out the tension first. But in the event that it did ask me to work out the tension, then this would be a better method. Okay, so, right. This, just to be clear what I'm saying, this bit is way easier because I don't need to worry about the tensions. But for the more difficult questions, you're going to have to consider the forces acting on the individual things. Right, I'm going to pause there and then think about question B.